Hello there, and welcome to Science to Sleep To, where we file the world into gentle, orderly folders and let your thoughts grow quiet at the edges. Tonight, on the desk in front of me, under the soft pool of a desk lamp, there is a thin folder with a dramatic title stamped across the tab. Cosmic Rays and High Energy Astrophysics. It sounds loud, explosive, like something that ought to come with crashing music and quick cuts between distant galaxies. But the truth is much quieter than that. Cosmic rays are not thunderclaps. They are not bright lightning bolts or obvious streaks in the sky. They are a constant, nearly invisible drizzle of tiny particles that has been falling through your body and through this planet for billions of years. They are always here, always arriving, a background whisper in the physics of everyday life that we rarely notice. For those who don't know, I'm Madeline Rowe, an astrophysicist turned private eye, and tonight I'll be your guide as we open this quiet case file on some of the most energetic particles the universe can make. This is Cosmic Rays and High Energy Astrophysics for Sleep. We will move slowly. We will take the long way around. We will start with a simple question. What is a cosmic ray, really? Then we will follow them into Earth's atmosphere, where one particle becomes an entire shower. We will drift over enormous observatories that watch for those showers in the dark. We will climb the energy ladder all the way up to the ultra-high energy events that still puzzle us. And finally, we will tuck everything into the wider story of high-energy astrophysics, where cosmic rays share the stage with gamma rays, neutrinos, and gravitational waves. Before we begin, if calm, deep dive science helps you fall asleep, a gentle tap on the subscribe button or a sleepy little like helps this tiny channel quietly keep going. You do not need to remember any of what follows. You do not need to stay awake for the end. Just let the details drift past, like distant radio static, while you rest. Let's start from the top. What is a cosmic ray? The name is a little misleading. Early researchers thought of them as a kind of mysterious radiation, a ray like X-rays or gamma rays. But today we know that most cosmic rays are not rays at all. They are particles. Most of them are just protons. A proton is one of the basic building blocks that sits in the nucleus of every atom of hydrogen. Mixed in with those protons are the nuclei of helium and heavier elements like carbon, oxygen, and iron. There is a smaller population of electrons and a tiny sprinkle of antimatter particles such as positrons. One way to imagine them is as a faint, invisible storm of microscopic bullets moving at close to the speed of light. That image sounds violent, but remember how empty space really is. Even inside your body, there is a lot of room for a particle to slip through without hitting anything important. Most cosmic rays pass straight through you, through your room, and out the other side of the planet without leaving a noticeable trace. So why do we care about them? Not because they are especially dangerous in normal amounts. We care because they are clues. Each cosmic ray carries a memory of where it was accelerated. It carries information about shockwaves, magnetic fields, explosions, and jets that we cannot visit directly. High-energy astrophysicists treat them as messages written in the language of particles and fields. One of the most striking things about cosmic rays is the enormous range of energies they cover. Energy here is simply a measure of how hard a particle would hit something if it collided. At the low end, there are cosmic rays that are only a little more energetic than particles produced in everyday processes in the sun or in our atmosphere. At the high end, there are particles whose energies are almost absurd. Consider the Large Hadron Collider, the ring of magnets near Geneva that accelerates protons to enormous energies. Now imagine a single proton in space with 1,000,000 times more energy than a proton in that collider. That is the kind of particle we classify as an ultra-high energy cosmic ray. If you plotted the number of cosmic rays against their energy, you would see a steeply falling curve. Low energy particles are common. High energy ones are rare. As you climb the energy ladder, you find fewer and fewer particles. That curve is not perfectly smooth. It has gentle bends and kinks with poetic names. At one point, the curve steepens slightly. This feature is called the knee. Higher still, the curve changes slope again at the ankle. And at the very top, it falls off sharply, where interactions with the cosmic microwave background start to sap the energy of the most extreme particles. These features are not just decorating a graph. Each bend hints at changes in the population of sources and the way particles propagate through space. The knee, the ankle, and the high-energy cutoff act like fingerprints for the processes that accelerate and scatter cosmic rays. If cosmic rays are tiny, invisible particles, how do we know they exist at all? The story begins in a balloon basket in the early 1900s. Physicist Victor Hess carried instruments that measured ionizing radiation and rose into the sky to see how the signal changed with altitude. Many people at the time believed that most of the radiation seen at Earth's surface came from radioactive elements in the ground. If that were true, the radiation should have decreased steadily as Hess rose higher. It did not. At first, the readings dropped a little as he left the immediate influence of the ground, but several kilometers up, the radiation began to rise again. By the time he reached his highest altitudes, the ionization rate was significantly higher than at the surface. Something was coming down from above. Today, we know that when a high-energy cosmic ray reaches Earth, it does not simply bump into the atmosphere and stop. It collides with an atomic nucleus high in the air and shatters it. That collision produces a spray of new particles, which in turn collide and decay to make even more. The result is an extensive air shower, a cascade of secondary particles spreading through the atmosphere. Some of those secondaries are muons, heavy cousins of the electron that are surprisingly good at punching through matter. Others are electrons, positrons, photons, and neutrinos. The shower grows, reaches a maximum, and then gradually thins out as energy is lost. From the ground, you cannot see this with your eyes. The sky looks ordinary. But if you are patient and build the right instruments, the shower leaves faint signatures that can be recorded. One method is to watch for ultraviolet light produced when the shower excites nitrogen molecules in the air. As those molecules relax back to their ground state, they emit faint fluorescence light. Large telescopes with wide fields of view stare at dark skies and look for those subtle streaks. Another method is simply to wait on the ground with an array of particle detectors. When the shower front reaches the surface, particles from the cascade pass through tanks of water or other materials and produce tiny flashes of Cherenkov light. Sensitive photomultiplier tubes record those flashes and their arrival times. By combining these two views, one from the atmosphere and one from the ground, scientists reconstruct the direction, energy, and sometimes the composition of the original cosmic ray. Now, one of the most impressive instruments built for this purpose is the Pierre Auger Observatory in Argentina. Imagine driving across a broad, flat plain under a dark sky. Every few kilometers, you pass a small, identical hut sheltering a tank of clear water with a light sensor inside. Each tank is quiet and self-contained, listening for passing particles. Together, these tanks form a grid that stretches over thousands of square kilometers. On nearby hills sit the fluorescence telescope buildings. When the night is clear and the moon is dark, their shutters open and their mirrors stare at the sky above the array. The atmosphere becomes part of the detector, a drifting screen on which cosmic ray showers briefly write their paths. Most of the time, nothing dramatic happens. There is background noise from faint airglow and scattered starlight. But every so often, a high-energy shower flashes through, triggering multiple tanks on the ground and painting a faint streak in the telescopes. Those hybrid events are particularly valuable because they combine two different kinds of information. In the Northern Hemisphere, the telescope array in Utah carries out a similar mission. It has its own arrangement of surface detectors and fluorescence stations, laid out across a high desert plateau. Together, Auger and the telescope array sample both southern and northern skies, quietly watching for the rarest, highest energy events. Once we know how to catch cosmic rays, the next question is where they are accelerated. For the lower energy and mid-energy population, up to around the knee, the main suspects live inside our own galaxy. Supernova remnants are among the strongest candidates. When a massive star explodes, its ejecta rush outward at thousands of kilometers per second, sweeping up the surrounding interstellar medium. A shock front forms at the leading edge of this expanding shell. Gas is heated and compressed, and magnetic fields are amplified and twisted. In this turbulent zone, charged particles wander back and forth across the shock. Each crossing gives them a small energy boost. Most particles are lost after a few cycles, but a minority manages to remain trapped long enough to climb to high energies. This process is known as diffusive shock acceleration. Over the lifetime of a remnant, a significant fraction of the explosion's kinetic energy can end up in cosmic rays. Those particles then escape into the larger volume of the galaxy, where they contribute to the diffuse cosmic ray population. Pulsars, the rapidly spinning neutron stars left behind by some supernovae, add another layer to this story. Their intense magnetic fields and rapid rotation set up huge electric fields along open field lines. Particles sliding along those structures can be whipped up to high energies and launched into pulsar wind nebulae. Magnetes, with even stronger magnetic fields, occasionally unleash powerful flares that inject energy into their surroundings. Although their contribution to the overall cosmic ray budget is still uncertain, they provide natural laboratories for extreme physics. We see hints of all this activity in gamma ray observations. When cosmic ray protons collide with gas, they produce neutral pions that quickly decay into gamma rays. By mapping gamma ray emission from supernova remnants, pulsar wind nebulae, and the galactic center, astronomers can trace the presence of energetic particles that are otherwise invisible. Now we climb to the top of the energy ladder into the realm of ultra-high energy cosmic rays. These are particles with energies above about 10 to the 18 electron volts, and in some cases up around 10 to the 20. Numbers like that are hard to hold in your head. It can help to remember the comparison with the Large Hadron Collider. A single cosmic ray proton can carry 1,000,000 times more energy than one of its protons. At such energies, even the low-energy photons of the cosmic microwave background become important. an ultra-high energy proton traveling through this sea of microwave photons can interact with them, producing pions and losing energy in the process. Over cosmological distances, this saps the highest energy tail of the spectrum, leading to a suppression known as the GZK cutoff. Observatories like Auger and the telescope array see a downturn in the cosmic ray spectrum at the highest energies, broadly consistent with this picture. They also see hints that the composition of the particles may become heavier at the very top end. That information feeds directly into our ideas about what kinds of sources could be responsible. Some models point to the jets of active galactic nuclei, where supermassive black holes at the centers of galaxies drive narrow outflows of plasma at nearly the speed of light. Shocks and turbulence in those jets can accelerate particles over enormous distances. Other scenarios involve the aftermath of gamma-ray bursts, the brief but intense explosions thought to be associated with collapsing massive stars or merging neutron stars. Their relativistic outflows may also host efficient acceleration zones. There are models in which rapidly rotating neutron stars or magnetars, especially newborn ones, act as colossal unipolar inductors, setting up huge potential drops that fling particles to ultra-high energies. And there are more exotic ideas in which ultra-high energy cosmic rays arise from the decay of super-heavy relic particles or from subtle modifications to fundamental physics at extreme energies. At the moment, the case is not closed. The data place constraints on these models, but do not single out one clear culprit. The highest energy part of the spectrum remains one of the most intriguing puzzles in high-energy astrophysics. One of the big challenges in using cosmic rays to trace their sources is that they are electrically charged. As they travel through galactic and intergalactic magnetic fields, their paths bend and twist. By the time they reach Earth, their arrival directions may no longer point straight back to where they came from. To work around this, modern high-energy astrophysics relies on multiple messengers. Instead of listening to a single channel, we tune in to several at once. High-energy gamma rays are one such messenger. They are produced when cosmic rays interact with gas or photon fields, and because photons are electrically neutral, they travel in straight lines through magnetic fields. Imaging atmospheric Cherenkov telescopes and space-based detectors map the gamma-ray sky, highlighting regions where particle acceleration is active. Neutrinos are another powerful, if elusive, messenger. They are produced in some of the same interactions that create gamma rays, but they barely interact with matter at all. They pass unhindered through dust, gas, and entire planets. IceCube, the neutrino observatory buried in Antarctic ice, watches for tiny flashes of light produced when a neutrino finally does interact. When a high-energy neutrino is detected, telescopes around the world can be alerted to look in that direction, searching for flaring blazes, tidal disruption events, or other candidates. And beyond particles and photons, there are gravitational waves. Ripples in space-time from merging black holes and neutron stars carry information about the most compact objects in the universe. When gravitational wave detections are combined with electromagnetic and neutrino observations, we get a richer, more cross-checked picture of extreme phenomena. Multi-messenger astrophysics turns the study of cosmic rays from a one-dimensional puzzle into a full, three-dimensional detective story. Each messenger supplies a different kind of clue. Put together, they help us slowly narrow down what is really happening in distant, high-energy environments. We have covered a lot of ground in this case file. We began with the simple idea that space is not empty, but filled with a thin rain of high-energy particles. We gave those particles an identity as mostly protons and nuclei, with a dash of electrons and antimatter. We climbed the energy ladder and noticed knees and ankles, gentle bends in the spectrum that hint at changes in sources and propagation. We followed a single cosmic ray into Earth's atmosphere, watched it trigger an air shower, and saw how huge observatories reconstruct its properties from faint flashes and pulses. We explored the likely role of supernova remnants, pulsars, and magnetars in filling our galaxy with cosmic rays. Then we stepped into the ultra-high energy regime, where particles rival or exceed the energies we can create on Earth, and where the origin of the highest energy events is still uncertain. Finally, we widened the frame to include gamma rays, neutrinos, and gravitational waves, turning cosmic ray science into part of a broader, multi-messenger story. By now, with any luck, all of this has softened in your mind. The violent events that give rise to high-energy particles are unimaginably far away. Their signals, by the time they reach you here, are faint ripples and tiny flashes. More like the distant murmur of a city heard through a window than anything urgent at your doorstep. As you lie here, there are cosmic rays streaming through the room. There are muons gliding down through the atmosphere. There are neutrinos passing straight through the Earth without stopping. There are gravitational waves from faraway mergers stretching and squeezing space-time by amounts far too small to feel. All of that continues whether you think about it or not. The universe does not need you to stay awake to keep it running. I am going to close the main file on cosmic rays for tonight, slide it back into the drawer, and turn the desk lamp down. The observatories will keep counting. The high-energy universe will keep humming quietly in the background. You are free to drift. This next file is a slower, more historical note. A walk through how we realised there was something coming down from space at all. Long before we used the phrase cosmic rays, people knew that there was invisible radiation around us. Simple electroscopes, with thin metal leaves that spread apart when charged, would slowly discharge even when carefully insulated. Something in the air was ionizing the gas and providing a path for the charge to leak away. At first, scientists blamed radioactivity from rocks in the ground or from building materials. To test that idea, some carried instruments into caves and down mine shafts, places where the rock overhead should shield them from radiation coming from above. The results helped, but they did not fully explain the patterns. The puzzle persisted. Victor Hess approached the problem from the opposite direction. Instead of going down, he went up. In a series of balloon flights, he carried ionization chambers to different heights in the atmosphere. If the radiation came mainly from the ground, the rate should have fallen steadily as he rose. But as we know, it did not. The readings dipped slightly near the surface and then climbed as the balloon ascended. Several kilometers up, the rate of ionization was significantly higher than at ground level. Hess repeated the experiment under different conditions, including during an eclipse, and consistently found the same upward trend. The conclusion was unavoidable. A substantial component of the radiation was coming from above. Over the following decades, as detectors grew more sophisticated, this mysterious, penetrating radiation became a playground for particle physics. Cloud chambers placed in magnetic fields and exposed to cosmic rays revealed curved tracks of unfamiliar particles. Muons, pions, and other short-lived species were discovered in this way. Imagine a small laboratory in the mid-20th century. A sealed chamber filled with supersaturated vapor sits between the poles of a magnet. Each time a charged particle passes through, droplets condense along its path, leaving a visible trail. Photographs of these trails reveal sudden kinks where particles decay, or neat arcs that betray their charge and momentum. Before we built huge colliders, the sky itself was our accelerator. Cosmic rays delivered high-energy particles to our detectors for free. As accelerators took over the job of discovering new particles, the role of cosmic rays shifted. Attention moved outward toward the astrophysical environments that launched them. The question changed from, "What is this particle?" to, "Where did this particle come from?" That shift laid the foundation for cosmic ray astrophysics as we practice it today. Between two of the thicker folders in the drawer, there is a slimmer one, its label written in smaller, tidier handwriting: Cosmic Weather in the Galaxy. If the earlier files are about individual raindrops, this one is about the climate they create together. When you zoom out far enough, cosmic rays stop feeling like individual particles and start to look like a kind of diffuse, invisible fluid. A sea of fast-moving charged particles threaded through the Milky Way, filling the spaces between stars, slipping in and out of clouds of gas and dust. In that picture, our galaxy is not just stars and gas and dark matter. It is also magnetic fields and cosmic rays woven together. The cosmic rays we see near Earth are only a tiny sample of a much larger population. Models of their propagation suggest that, on average, each cosmic ray spends millions of years wandering through the galaxy before escaping into intergalactic space. In that time, it may collide with atoms in interstellar clouds, producing gamma rays and secondary particles. It may bounce through magnetic turbulence in spiral arms and superbubbles carved by clusters of massive stars. If you could see cosmic rays the way you see light, the Milky Way would not look dark between its stars. It would glow gently, a murky, speckled haze, strongest where star formation and supernova explosions are most active, weaker out in the quiet outer disk and halo. Cosmic rays do more than passively drift. They push back. Because they move so fast, they carry pressure. When cosmic rays encounter a region of higher gas density, they scatter and exert a kind of gentle outward force. That pressure can support gas against gravity, help shape the thickness of the galactic disk, and, in some simulations, drive winds that carry material out into the halo. It is a very slow, very subtle process. No single particle does much, but trillions upon trillions of them, integrated over millions of years, can change how gas circulates and where new stars are born. Observers see hints of this in the way gamma-ray brightness varies across the sky. Certain regions, especially near the galactic center and in massive star-forming complexes, are brighter than you would expect if cosmic rays were perfectly uniform. That suggests that the cosmic ray weather has storms and gradients, high-pressure systems, and calmer zones. Theoretical models describe this in terms of diffusion coefficients and streaming instabilities and detailed transport equations. On the page, they look like dense forests of symbols. In your mind, you can translate them into something simpler. A sea of charged particles, always jostling, nudged by magnetic fields, trying to spread out evenly, but continually stirred by new injections from shocks and flares. Here and there, a recent supernova remnant may still be surrounded by a bubble of slightly higher cosmic ray density, a fading echo of more intense acceleration. Farther away, near the outskirts of the disk, the sea is thinner and cooler. From the perspective of a single proton, none of this structure is visible. It simply follows its tangled path, taking whatever turns the fields dictate. From the perspective of the galaxy, cosmic rays are one more ingredient in a large-scale recipe, helping to determine how matter, energy, and magnetic fields share the space between stars. It is an odd kind of weather to think about as you fall asleep. No clouds, no raindrops, no storms as we normally imagine them. Just a long, slow, invisible wind of high-energy particles blowing through the Milky Way for billions of years. The next file zooms in on one event, one cosmic ray, one shower. Imagine a proton that was accelerated long ago near the shock front of a supernova remnant. It bounced across the shock many times, stealing a little energy on each pass until it finally escaped into the wider galaxy. For millions of years, it wandered through interstellar space. Its path was not a tidy, straight line. It spiraled around magnetic field lines, scattered off irregularities, and drifted slowly from one region to another. Eventually, by chance, it entered the outskirts of the solar system. The solar wind and the sun's magnetic field tugged at its trajectory, but not enough to turn it completely aside. On a quiet night, it happened to be aimed toward Earth. High above the planet, tens of kilometers up, the proton collided with a nucleus of nitrogen in the atmosphere. In a fraction of a second, its energy was poured into an explosion of new particles. Pions and other hadrons flew away from the collision point. Neutral pions decayed almost instantly into gamma rays. Charged pions travelled a little farther before decaying into muons and neutrinos. Those products interacted and decayed in turn. The single proton had become a branching cascade. As the shower moved downward, the number of particles grew. Electrons and positrons multiplied in an electromagnetic subcascade, radiating photons that produced more pairs. Muons, more massive and more penetrating, streamed ahead, many of them surviving long enough to reach the ground. The shower reached a maximum at a certain altitude, then slowly thinned as particles lost energy and were absorbed. On the ground below, a grid of detectors lay in wait. In one tank of water, a muon passed through and emitted a cone of Cherenkov light, like a tiny blue shock wave. A photomultiplier tube caught the flash and marked the time. A fraction of a microsecond later, another detector recorded its own flash. Then another. The shower front swept across the array, lighting up stations in a pattern that reflected its direction and energy. In a nearby building, a fluorescence telescope registered a faint streak in the sky, tracing the shower's development through the atmosphere. When analysts later combined these signals, they reconstructed the energy of the original proton, its arrival direction, and an estimate of its mass. For the proton, the entire journey from the edge of the atmosphere to the ground lasted a very small fraction of a second. For the observatory, it became one line in a vast dataset. For you, listening now, it is just a passing image in a story that you are free to forget the moment sleep arrives. There is also a folder in the drawer with a tab that simply reads Other Worlds. Up to now, we have been following cosmic rays as they interact with Earth's atmosphere and with our detectors on this planet. But the rain of high-energy particles doesn't stop at our sky. It falls on other worlds too, each with its own way of receiving it. Start with the Moon. The Moon has no global magnetic field and only the thinnest wisp of an exosphere. There is no thick blanket of air to turn a single proton into a large cascade. When a cosmic ray reaches the lunar surface, it mostly hits rock. Those collisions still produce secondary particles, but they happen in the upper layers of the regolith instead of high in a gas layer. Over billions of years, this constant bombardment has gently modified the chemistry and structure of the lunar soil, creating a skin of material that has been baked and milled by radiation and micrometeorites. If you picture an astronaut standing on the moon's surface in a bulky suit, the cosmic ray rain is falling steadily around them, most of it unseen, some of it registering in radiation monitors, all of it part of the environment that future lunar bases will need to account for. Mars is somewhere in between Earth and the Moon. It has an atmosphere, but it is thin. Its magnetic field is patchy, remnant, not the strong global shield we enjoy. Cosmic rays reaching Mars penetrate deeper before producing showers, and more of the primary particles make it close to the surface. For robotic missions, that radiation is just another engineering constraint. For future human explorers, it becomes part of the life support budget. Habitat walls, water tanks, and regolith piles can all help blunt the flux, turning the raw cosmic weather into something more manageable. Farther out, the giant planets introduce their own complications. Jupiter, for example, has a powerful magnetic field that traps charged particles and accelerates them to high energies in its radiation belts. Some of those particles began as cosmic rays, captured and reprocessed by the planet's magnetic environment. The result is a harsh space weather system, one that spacecraft must tiptoe through. Saturn, Uranus, and Neptune each have their own magnetospheres and interactions with the cosmic ray sea. Even dwarf planets like Pluto and large moons like Ganymede feel the rain in ways that depend on their local fields and thin atmospheres. Outside the heliosphere, beyond the reach of the solar wind, the spectrum of cosmic rays becomes a little different again. Spacecraft like Voyager have tasted that change as they crossed the boundary region, seeing a rise in the flux of lower energy particles that are held back closer in. And beyond our solar system, exoplanets orbit under their own balance of shielding and exposure. A rocky world with a weak magnetic field, close to an active star, might be bathed in flares and cosmic rays that strip its atmosphere or alter its chemistry. A world with a strong field and a thick atmosphere might deflect and absorb the bulk of the rain, turning it into soft glows of aurora and faint flashes high above the surface. We do not yet have detailed maps of cosmic ray conditions for those distant worlds. For now, they are mostly theoretical possibilities, explored in simulations and models. But as we learn more about stellar activity, magnetic fields, and atmospheric escape, cosmic rays will remain part of the story we tell about which planets are calm, which are stormy, and which may be hospitable to life. From your vantage point, lying in bed on Earth, these differences are easy to blur. One universe, one cosmic ray sea. But in the fine print, each world writes its own version of how that sea shapes its surface, its sky, and any future visitors who might one day stand there and look up. Another file in the drawer is a quiet tour of the observatories that listen to the high-energy universe. First, we drift back over the Pampa Amarilla, where the Pierre Auger Observatory spreads its grid across the landscape. From above, the tanks look small and regular, each one a tiny outpost with its own power supply and communication link. At night, technicians might see a faint glow from status lights, but mostly the detectors sit in darkness, listening. In the fluorescence buildings, mirrors and cameras point out through open shutters when conditions are right. The telescopes see nothing like a normal photograph. Instead, they record short, streak-like tracks of ultraviolet light against a black background. Each track is a shower. Most are modest, a few are impressively bright. Thousands of kilometers away, the telescope array in Utah performs a similar watch. Its detectors are separated by desert scrub and low hills, under a sky that can be exceptionally clear. Together, these two experiments form a kind of binocular vision for ultra-high energy cosmic rays. Higher still, satellites like Fermi orbit the Earth. They do not see showers in the atmosphere. Instead, they record tracks inside their own detector volumes, as incoming gamma rays convert into electron-positron pairs. By reconstructing those tracks, they map the high-energy gamma-ray sky. On mountaintops, imaging atmospheric Cherenkov telescopes such as HESS, MAGIC, and Veritas point large mirrors at the sky. Fast cameras at their focal planes capture extremely brief flashes of Cherenkov light from air showers triggered by gamma rays. The images they record look like blurred, lopsided ellipses. The orientation and shape of each ellipse carries information about the direction and energy of the incoming photon. And deep below the Antarctic surface, IceCube listens to the faint pings of light from neutrino interactions in the ice. Its optical modules hang in the darkness like strings of softly glowing beads. Most of the time, they see only the gentle background of atmospheric muons and noise. Occasionally, they record patterns that trace back to neutrinos from the far universe. If you picture all of these facilities together, they form a loose, planet-sized network. Plains, deserts, mountaintops, orbiting satellites, and buried detectors all share the same quiet task. Watch, record, wait for patterns to emerge over years and decades. Tucked beside the observatory folder is another, filled not with photographs of tanks and telescopes, but with printouts and plots. Its label is simple: analysis. It is easy to imagine that the story ends when a detector clicks or a telescope records a streak of light. In reality, that is where another, slower story begins. When a shower passes over a surface array, the first thing that appears is not a neat entry in a catalogue. It is a set of raw signals, pulses of voltage from photomultiplier tubes, timestamps from electronics, status information from weather stations and calibration lasers. These arrive at a central computer as streams of numbers. Many of them are mundane. Some are clearly just noise, a lightning strike nearby, a glitch in a power line, a momentary hardware hiccup. Others are consistent with the constant background of lower energy showers that pepper the detectors all the time. Buried among them are the events the collaboration cares most about: higher energy showers, well contained in the array, with clear footprints and good atmospheric conditions. The first stage of analysis is sorting. Triggers select which combinations of station hits are worth saving. Quality cuts decide which events are good enough to use in later studies. Calibration procedures convert raw voltages into physical signals, correcting for variations in detector response, changes in temperature, and the aging of components. On the fluorescent side, the process is similar but tailored to a different kind of data. Cameras record images of the sky in short time slices. Software identifies tracks that move like showers rather than stationary stars or random noise. Atmospheric monitoring systems, including lasers and LiDAR, track how transparent the air was at the time, so that corrections can be applied for scattered and absorbed light. Once individual events are reconstructed, they must be translated into physical quantities: arrival direction, core location on the ground, energy estimate. depth of shower maximum. Each of those steps carries uncertainties and assumptions, which are tested against simulations. Simulations play a quiet but central role. They fill in the gap between what the detectors see and what theory predicts. By generating artificial showers with different energies, compositions, and arrival directions, and then passing them through a virtual version of the observatory, scientists can see how well their reconstruction methods perform and how biases creep in. Only after this loop between data and simulation has run many times do the summary plots begin to take shape. Energy spectra with error bars, sky maps showing arrival directions, distributions of shower depth that hint at whether the primaries are mostly light nuclei, like protons, or heavier ones, like iron. Even then, the story is not finished. Collaborators meet, often in large rooms or video calls that span continents and time zones. They compare independent analyses from different groups to see whether the same trends appear. They argue gently about which interpretation best fits the results. They draft internal notes, then conference talks, then journal papers. From the outside, a paper might look like a clean, finished object. A few plots, some equations, a conclusion about spectral slopes or composition. Inside the collaboration, each of those curves represents months or years of careful work by students, postdocs, engineers, and senior scientists. If you pause to imagine a late night in one of those offices, the scene is not so different from this quiet desk with its lamp and folders. Someone leans over a keyboard, scrolling through lines of code. They tweak a selection cut, rerun a fit, check a residual plot. Outside, the sky is clear and full of showers the detectors are silently catching. Inside, a single person is trying to make sure the way they summarize those showers is honest, robust, and genuinely telling us something new. While you listen, the raw data keeps streaming in. Somewhere, disks are filling with numbers that will not be fully analysed for months or years. The universe is in no hurry. The analysis does not need your attention right now. It is perfectly happy to proceed at its own careful pace while you sleep. The next file returns to a more imaginative viewpoint. We will ride along with a cosmic ray during its long, meandering journey. Picture a newborn neutron star, the core left behind after a massive star's collapse. It is hot, dense, and spinning rapidly. Its magnetic field is trillions of times stronger than the field at Earth's surface. In the magnetosphere around this neutron star, electric fields appear along open magnetic field lines. Charged particles feel those fields and are accelerated to high energies. Imagine one proton caught up in this process. In our mind's eye, we perch on its back as it surfs along a field line, spiraling rapidly while gaining energy. At some point, it escapes into space, flung outward into the surrounding nebula. From there, its path becomes a wandering thread. It is guided and deflected by magnetic fields on many scales. It might loop around the neutron star's host supernova remnant for a time. It might drift into the broader galactic magnetic field and begin a long random walk through the Milky Way. From our proton's perspective, time passes, but there is little to see. The galaxy is mostly emptiness. Fields and occasional clouds of gas are the main landmarks. Over hundreds of thousands or millions of years, it gradually migrates from one region of the galaxy to another. Sometimes it moves closer to the galactic center, where fields and densities are stronger. Sometimes it drifts toward the outskirts. Eventually, by sheer chance, its random walk carries it into the local spiral arm where our sun resides. The heliosphere lies ahead, a bubble carved out by the solar wind. As the proton crosses the boundary of this bubble, it encounters the sun's magnetic field lines and the churning plasma of the solar wind. Its path bends and oscillates again, but this time the region is small compared to the galaxy. Within a relatively short time, it finds itself pointing toward Earth. From here, the story merges with the air shower narrative we already followed. A collision in the upper atmosphere, a cascade of particles, a cluster of faint flashes in ground-based detectors. A journey that lasted millions of years in space ends in less than a second in the air above a detector array. You might be falling asleep on the other side of the planet when it happens. You never feel it, but somewhere in a file on a server, a few numbers describing that event are quietly added to a growing catalogue. Near the back of the cabinet, there is a drawer that sticks just a little when you pull it. Inside are notebooks rather than case files. Their pages are filled with lines and curves instead of paragraphs. On the tabs, someone has written "Spectrum" on one and "Next Experiments" on another. When scientists talk about the cosmic ray spectrum, they are compressing enormous complexity into a simple picture. On one axis, you mark energy. On the other, you mark how many particles arrive with that energy per unit area, per unit time, per unit solid angle. Plot it on ordinary linear scales, and almost everything of interest collapses into a tiny region near the origin. The numbers span too many orders of magnitude, so instead, the axes are stretched in a different way. Both energy and intensity are often shown on logarithmic scales. Equal distances along the axis correspond not to equal steps in energy, but to equal factors of 10. A straight line on such a plot means this quantity follows a power law. For cosmic rays, the spectrum over wide ranges of energy is close to a power law, with an index around -2 point something. In plain language, that means that if you double the energy, the number of particles at that energy drops by a factor somewhere between 4 and 8. Increase the energy by a factor of 10, and the flux falls by roughly 1 or 2 orders of magnitude. Those neat, straight-ish segments are part of what make cosmic rays so attractive to theorists. Power laws often emerge from stochastic acceleration processes like diffusive shock acceleration. They hint at scale-free behavior, no single preferred energy, just a continuous hierarchy from the common and modest to the rare and extreme. The knees and ankles we talked about earlier show up in these log-log plots as gentle changes in slope. Fitting those slopes and determining where they change and by how much is one of the main tasks of spectrum analysis. Each bend carries information about the balance between different source populations and about how particles lose energy or escape as they propagate. In the notebooks in this drawer, you might imagine page after page of such plots, each with slightly different assumptions. Different hadronic interaction models for the showers, different composition mixtures, different treatments of the atmosphere. The aim is not to make the spectrum look smooth and tidy, but to understand where the uncertainties come from and how robust each feature really is. Next to the spectrum notebook is the one labelled Next Experiments. No single observatory can watch the whole sky at all energies. Each has its own sweet spot and limitations. To keep improving our picture, new instruments are designed to fill gaps and cross-check existing results. Some upgrades are evolutionary. The Pierre Auger Observatory, for example, has been enhanced with additional detectors and electronics in an upgrade known as Auger Prime, designed to improve its ability to distinguish between light and heavy primaries at the highest energies. fluorescence telescopes gain better calibration systems. Surface arrays add scintillators or radio antennas that provide complementary information about the shower. Other projects are more radical. Plans for next-generation radio arrays aim to detect the radio pulses generated by air showers with enormous effective areas, using networks of antennas spread over large regions or piggybacking on existing facilities. In the right configuration, these could catch ultra-high energy events that are too rare for smaller instruments to see often. Space-based concepts imagine satellites watching vast swaths of the atmosphere from above, looking for the faint flashes of fluorescence from showers developing in the air below. From orbit, a single instrument could, in principle, monitor areas larger than entire countries. In neutrino astronomy, designs like an expanded ice cube or other detectors in water and ice promise to increase the number of high-energy neutrinos we can detect by large factors. That, in turn, would sharpen our view of which cosmic accelerators are efficient neutrino factories and which are quieter. Gamma-ray astronomy is moving toward arrays of telescopes of different sizes, such as those planned for the next generation of Cherenkov observatories, to cover a broader energy range with better sensitivity and resolution. Taken together, these future eyes and ears are not about making the sky look more dramatic. They are about making it clearer and quieter in a scientific sense, reducing uncertainties, resolving conflicting measurements, and turning tentative features into solid knowledge. From your perspective, they are also a kind of reassurance. The questions this episode has raised: where do the ultra-high energy particles come from? How exactly does the spectrum bend and change? What role do cosmic rays play in galactic ecosystems? Do not need to be solved tonight. Designing, building, and operating these observatories is a long, patient process. Proposals are written, prototypes are tested, sites are surveyed. Only years later do the first data begin to flow. Somewhere, right now, people are sketching ideas for instruments that may not see first light until long after you have finished listening to this episode. They will be ready to take over the watch when current observatories eventually retire. The universe is generous with time. The answers will come, bit by bit. You are allowed to let the details go blurry, knowing that someone, somewhere, is keeping a careful eye on those slowly evolving plots in the Spectrum notebook, even while you sleep. The last file in the drawer brings cosmic rays closer to everyday life, and then out again to the edge of theory. Even if you never visit an observatory, cosmic rays touch your world in small, practical ways. If you have ever taken a long-haul flight, especially at high latitude, you have spent hours at an altitude where the cosmic ray flux is higher than at sea level. The extra dose of radiation is still small compared to medical exposures, but it is measurable. Airlines and regulators account for it when they track occupational exposure for crew members. In electronics, cosmic rays occasionally cause single-event upsets, flipping bits in memory or logic circuits. Error-correcting codes and redundancy help catch and fix those flips, but their existence is a subtle reminder that the high-energy universe can reach right into your devices. Engineers and geophysicists also make creative use of cosmic ray muons. Because muons are penetrating, they can pass through thick layers of rock. By placing detectors around a structure and measuring how many muons make it through from different directions, scientists can build up an image of dense and less dense regions. This technique, called muon tomography, has been used to study volcanoes and to look for hidden spaces in pyramids. From there, we step back out to the frontier of theory. Ultra-high energy cosmic rays reach energies far beyond anything we can produce in human-made accelerators. That makes them valuable probes of fundamental physics. By studying the spectrum and composition of these particles and how they change with energy, physicists test models in which super-heavy relic particles from the early universe decay into observable cosmic rays. If the data deviate from what we expect from conventional astrophysical sources alone, it could hint at new physics. There are also scenarios in which tiny departures from exact Lorentz invariants would reveal themselves in the behavior of ultra-high energy particles. For example, certain interactions might become allowed or forbidden at very high energies, slightly altering propagation. So far, observations have placed strong limits on such effects, but the search continues. In parallel, connections between cosmic rays, gamma rays, and neutrinos provide ways to probe the environments where dark matter particles might annihilate or decay. A small, consistent excess in one of these channels, carefully cross-checked against astrophysical backgrounds, could point to particles beyond the standard model. None of these possibilities are guaranteed. They are hypotheses waiting for data to confirm or reject them. High-energy astrophysics advances one careful step at a time. For you, lying here listening, the most important part is that this process is gradual. There are no sudden shocks that demand your immediate attention. Cosmic ray research is more like a long conversation, slowly unfolding between experiment and theory. You are allowed to let that conversation continue in the background while you sleep. Somewhere, detectors are counting particles. Somewhere, code is fitting spectra. Somewhere, a researcher is staring at a plot, wondering whether a tiny feature is real or just noise. You do not need to be part of that vigil tonight. You have done enough for one day. Let the high-energy universe keep racing around at almost the speed of light. Let the cosmic rays do the traveling and the detectors do the thinking. Your only job now is to breathe slowly. Let your thoughts wander and sink into sleep. Sleep well.